You see? I cannot.
You want me to put it in?
Yeah,
Okay, thank you.
I mean, I can do it for you.
No, it means touching me. Guys, there is no, I'm not on the, it's just for recording. It's not going to the speakers and everything. So thank you very much for coming. My name is Yossi Taguri. I'm the CEO of Missing Link AI. And I want to first thank, do you know where you are, by the way? Yeah, some of you know, like the alumni of MIT Media Lab knows. But this place hosts around between 20 to 30 groups of people, maybe the smartest, the most creative, and most humble people alive today. You will get to see some of them today. And they create things. Last week there was a members event where they did demo days of everything that they're creating here. And I have to say this was one of the most inspiring events I've ever attended. Goes far beyond TED. You just see young people, super creative, that are not just learning about the world, but also contributing and acting to make it better. This place invented 3D printing in this building, right? 3D printing. All the 3D printers that you know started here. They also invented printing on glass. They invented force feedback that you probably know. They invented active limbs. How do you call it? Active prosthetic legs that actually connect to your nerves and act. They're active, they're not passive, which is insane. And they have like dozens of inventions that you might be able to see some of them through the classes. So thank you very much for Tal Achituv, who was a kind of a CTO to the Media Lab that is hosting us today. We actually, don't tell anyone, we hijacked the place. It was not, they did not know that we're going to do, but it's after 6 p.m., so nobody's here, we're fine. So my name is Yossi Taguri. I am 45 years old. I'm pretty old. One thing you don't know about me is that I have 4 daughters. I tried having boys, didn't work out so well. I have 4 girls. And 2.5 years ago, I started a new company. But I started that company because my previous company before that, I got to do quite a lot of deep learning. Now you need to understand, I am not a data scientist. I am an engineer. I started coding at the age of 11 when there was 8 bits computers and 64K of memory. Do you remember the Commodore 64? Anybody even knows what the Commodore 64, right? Yeah, all the old people knows what the Commodore 64 is. It's awesome. So I got this computer and you get it and it's a keyboard and you connect it to a piece, to a monitor. There's no joystick, there's no operating system. It just blinks and it expects you to write code. Now, as an 11-year-old kid, what do? You start to break things, and you fix them, and you learn how this machine works. That's how I spent most of my childhood breaking things and learning how to fix them again. But in my previous company, we had a lot of data. We had telephony data. We had phone calls going through us all the time. And we started asking questions. What can we do with that data? And one of the ideas that we had is, what if we will be able to predict what happens 30 minutes into the future of a call? What if a salesperson is sitting and is trying to sell something to somebody else, and we will be able to predict 30 minutes into the future whether it's going to work or not, right? Now, I'm an engineer, a software engineer. I'm no data science. I barely got my BSc in computer science because my wife has a PhD. She helped me a bit do the math homework. I promised to my mom that there will be a Dr. Taguri. I just married one. It's the best shortcut ever. And I asked, how do I solve such a problem? And I met PhDs, I met professors at the universities in Israel, and they all told me one thing. You have to do what we call feature extraction, and then you feed it into this statistical model, and then you might get some kind of an answer. But doing that feature extraction is something that, you need to be a PhD. Let's be honest about it, right? Who has a PhD in the room? 1, 2, 3, 4, amazing. And all the rest are doing deep learning without, or machine learning without it. That's pretty impressive. So by complete mistake, I stumbled upon this post. The unreasonable effectiveness of recurrent neural networks. Who knows this? Right? Almost everybody knows this. I read this blog post. What it does, the guy that wrote it was Andrej Karpathy. Andrej Karpathy is today the head of AI at Tesla. You probably saw him at the last week announcement with Elon Musk on stage explaining why deep neural networks are the best thing ever for computer vision and autonomous cars. But he wrote it 4 years ago when he was a student at Stanford, and he created the first, before he created the course, he created this post. And this post basically goes on to, without any math whatsoever, he explains how the recurrent network works. Now I'm reading this, and it's around maybe 60, 70 lines of code of Python. And this code basically absorbs a lot of data, maybe sometimes it's text, and it spits out a similar text. You all know that it's pretty common these days. And I think this is the first time that I saw a program that learns from data and not just by algorithms. There's no spec. There's not an engineer that writes an if-then else and try to cover all the possible problems. This is just 60 lines of code that has no knowledge whatsoever about the data it's about to get, and still it's able to mimic English, to mimic any kind of structure, even, by the way, if I'll go take you downstairs, even C code. They fed it the kernel source code for Linux, and it spit a new source file with the comments and with the includes, and it knew that if it has a for and then just one line of code and it doesn't need curly braces, it actually learned the structure of the language without any definition. Now, as an engineer, it blew my mind. I never seen a technology that could do that. I'm used to structuring my problems, breaking them into smaller problems and coding everything, and suddenly this came in and changed everything. So I stopped everything that I did, and I found out that this guy is doing a course, CS231N. If you haven't done it, this is maybe the best course ever for it's actually for PhDs, but for non-PhDs to get into deep neural networks. You do not need to know anything about statistics, anything about math. If you know how to multiply two matrices in linear algebra 1, which you probably know, this is enough to graduate that course. So I took it, and he basically teaches you how deep neural networks works. And I stopped my company, I stopped all the engineering in the company, and I asked, please go to YouTube, see CS231N, 18 courses of 1.5 hours each. If you play it on 1.5 speed, you can still understand what's going on, but you will know how to create. You will understand the mechanics of how it works. And we try to do it. We are engineers. We're used to, committing things, and everything is automatic, and everything runs and ships to production, and everything is tested automatically. And we try to do the same with deep neural networks, and we found out that it's quite hard. It's not as easy. I felt like going from a super automatic process, I went back in time 30 years back to the Commodore 64 days where I'm alone with a keyboard and I need to know what's going on. Suddenly I need to SSH into machines. I need to parse logs. I need to understand what I'm doing. I cannot run 500 experiments in parallel because it's simply impossible. So we created a company called Missing Link that basically does all that. But before I give the stage to other amazing people that we have in the room, I wanna just a little personal story. This is my mom, right? My mom is called Victoria, Vicky. She was born in Morocco, right? I'm half Moroccan, half Libyan, which is a bit strange. It's the best food in the world. And 9 months ago, we found out that she is sick with non-Hodgkin's lymphoma. This is a very aggressive cancer, treatable, but very, very aggressive. Now, when you do CT scans, you do MRI, you do all sorts of things, and I was looking for a doctor that would be able to look on that CT scan, on MRI, and tell me, what do we see here? What is that? And I couldn't. I was willing to pay any amount of money in the world just to have 10 minutes with a doctor that would tell me what am I against. That is it. And the funny story is, we have a customer in Missing Link called AI Doc that does exactly that. They scan CT scans and they draw the attention of a doctor to a pixel that could be something one day, and that's what they could do. But I couldn't use them because the hospital that we were treated at didn't have that system. So as far as we think that, as long as we think that we're very, very advanced, that we have almost autonomous cars and we have medical companies that can treat us and everything, we are still at the tip of the possibility of what can be done. It is my mission and our mission at Missing Link to empower companies that change the world to actually make it much, much better. I think you will agree with me that you will probably live a lot longer, not just because of advanced medicine, but because of also early detection of things, right? Today we're just scraping the tip of the things. So without further ado, by the way, my mom is actually this week getting the last treatment, and her tumor disappeared like it came, and it seems that everything is going to be all right, so we have a good, at least a good ending with this. I would like to pass the stage to Matt DiNardo. Matt? Yes. Yes, who's working for Hopper. One fun fact about Matt, he's playing the cello, right?
I do play the cello.
You do play the cello. And it was not, nobody forced you to play the cello. You liked it.
Early on. But
early on, yeah. So if you do not know Hopper is one of the more exciting companies out there. They have a big office in Boston with amazing and insane amount of data scientists working, right, under Ella. Everybody is under Ella?
Yes, under Ella, yeah.
Under Ella, and they're doing crazy things. Now, how many of you know Hopper? Right. So I think I'm getting you new customers today, which is awesome. So if you don't know Hopper, just download it and it will show you in a few minutes what it is.
Yeah, absolutely. Thank you for that awesome introduction. Yeah. So for those of you who don't know Hopper, we're a travel app. And are we showing up here? Uh-oh. Let's see if this is a second.
The HDMI cable, make sure it's stuck all the way in.
Yeah, it is now. We're good.
Okay, great. Yeah. So it sounds like a lot of people in here are familiar with Hopper, which is great. I love our app and people love our app. But for those who don't know, Hopper is a mobile-only travel app, and that allows users to book their travel, flights and hotels on mobile, on their phones. But really the main value proposition that Hopper provides users is we help alleviate a lot of the uncertainty that comes with travel planning. And part of the way we do that is through our targeted recommendations. So one of our main value propositions is we will provide a recommendation on when you should book your flight in order to save the most money. So basically, I think if you're a traveler, you know that one of the things you worry about when you're booking your travel is, are you getting a good deal on your flight? Nobody wants to be the one who paid the most money for their ticket on their plane. But actually, if you're on a plane, chances are you paid a different price than almost everybody sitting around you. So there's a kind of a general anxiety there where we have users who want to make sure that they're getting a good deal on their flight. And on the other end of the spectrum, flight prices themselves are actually quite volatile, even over a longer period of time. So to explain this visualization a little bit, on the bottom axis here, you have the return date of a trip. On the top axis is the departure date. And then the diagonal is sort of like the length of that trip. So every point on here is a unique trip, and the color scaling reflects the actual price of the trip. So this is showing essentially the volatility in prices for trips, even within a single day. So there's a general rule of thumb, which is the further out you are, the better off you are booking early. And that's true to some extent, but there's enough volatility such that even if you're far out, it's good to have a historical data set or have some sort of recommendation system that can really make sure that you're getting a good deal on your flight. So today I'm going to talk about an application of sequence-to-sequence learning to assist with our time series forecasting problem. And but first I want to talk a little bit about what that actually looks like to the user. So basically the user using our app sees this screen on the right, They enter an origin, a destination, a departure date, and a return date. And Hopper gives them the best, the current best price to book for that trip, as well as our recommendation on whether they should book now or wait. And if they choose to wait, then we will periodically, automatically shop for trips for that route. And then when we find a price that's good, we will send a push notification to the phone saying, we found this price, this is a good price, so you should book now. And on the left here, we just have a histogram of the savings we provide users. We capture about half of the savings that are possible with the timings that users tend to have. One of the interesting things is that the average person tends to search about 60 days out before departure for their flight, but Hopper users actually look earlier. They look about 90 days out on average, which is good for airlines. It's good for us because we have more time to help them find a great price. But the big question is, how do we actually do this forecasting? And the short answer is the way we do it is with a lot of data. Our historical flights archive consists of about 15 trillion price quotes going back 5 years. And the right side of the screen here is basically what the user sees. Is that the user sees our estimation of how prices are going to fluctuate from the current point until the departure date. And the left is basically what's happening in the background. And there's a lot going on here, but the two things to kind of point out are the blue dots are essentially the best prices for that specific trip on that date. And this is actually a trip from Boston to Cancun. So every single one of those blue dots represents an actual price we got for that. The green line is the other component to keep in mind. That's essentially our expectation of the price trend from today going until the departure date. So broadly speaking, basically what we do is we look at our historical archive to develop some sort of expectation about what the price trend is going to look like, and then we update that expectation based off like real prices we're actually seeing. So the question becomes, how do we incorporate those blue points to adjust our predictions going forward? And overall, the system works because there exists predictable seasonality in a lot of these routes. So for example, Boston and San Francisco has pretty reliable year-over-year seasonality, and that seasonality tends to be pretty intuitive. So if there is a cold winter origin and a warm winter destination, then seasonality for demand tends to reflect that as well as prices. So one of the reasons that this works is because there is this predictable seasonality. On the flip side, part of why it's hard is because this seasonality varies with every route. And we're trying to make a prediction that generalizes to tens of thousands, hundreds of thousands of routes. So you can't rely on like a single estimate of what seasonality is because it's different route by route. So on the bottom right here, what you really see is that the typical advance curve from Newark to Boston looks very different from Newark to Honolulu. So developing a learner that is able to generalize to all these different routes is a very significant challenge. And one of the deep learning approach that we are experimenting with to basically help achieve this is sequence-to-sequence modeling, which you may be familiar with or you may not be familiar with. This is actually a callback to the blog post that was just mentioned in that same blog post. And in the blog post, it mentions that one of the limitations of the traditional neural network is that it takes a fixed size input vector and it generates a fixed sized output vector. But with our problem, we have potentially many inputs, potentially few inputs. We have a sequence of inputs, and we also want to predict a sequence of outputs. We want to predict the price periodically from today until the departure date. So the traditional neural network doesn't really work for us, which is kind of what you see on the left here. So we look towards recurrent neural networks and an architecture called sequence-to-sequence learning, which is actually right here where my mouse is, where you see the red blocks are the inputs, and they map to potentially many outputs, which are the blue blocks here. So I don't have time to go over like a neural network. If that's new to you, this blog is an excellent intro to it. But basically, there are three components of a sequence-to-sequence model. There's first the encoder, which is kind of like its own part of the architecture. And the encoder basically learns to take a variable length sequence input and map that to a single fixed length vector, which is exactly what we want to do. Because kind of going back here, we have all these blue dots, we have all these samples, and we want to map that to a single context, in which case this context is a single fixed length vector. And then we want to take that fixed length vector and unravel it over potentially many steps. So you can see this is a good approach because we have cases where we're trying to make a prediction from very far out. So we're trying to make a lot of predictions with not a lot of data, especially on routes that aren't very popular. We don't have a lot of those blue dots. Sometimes we only have 3 or 4. Sometimes we have a lot of dots. So in any case, we need a learner that lets us feed in potentially variable length sequences like this and create a context that we then use to actually power our predictions. So this is what we've been experimenting with, and it's been quite effective, and we're looking forward to experimenting with it more. But to provide kind of some more context, a traditional ARIMA model might be like a good initial thought for a problem like this. But again, getting back to the seasonality, the routes are so different that you can't fit hundreds of thousands of different ARIMA models, or you could try, but it wouldn't be that great. So this architecture just gives us more flexibility to create one model that generalizes to a broader set of trips. This approach also allows us to like actually feed in additional numerical or categorical features, and those all are basically encoded into like that single vector that provides context. And overall, kind of like the intuition behind this approach makes sense, is that we're trying to predict next values conditioned on like the previous values and our previous predictions. So the way it actually ends up working, and if I go back here, is in the decoder output, we actually feed the predictions as inputs to the next step of the prediction. So what you get is you get these smooth predictions, and the neural network learns not to make crazy predictions because otherwise it'll drift away. So in this case here on the right, the green are the predictions being made by the sequence-to-sequence model. The yellow dots are the input sequences given to it, and the red are what it is trying to predict. So you can see with one model, we're able to predict an entire sequence up until the departure date, and this really helps us deal with the fact that sometimes, like these yellow dots, we can shrink or expand the window to try to get more context, and we can also work with cases where there's sparse data. Yeah, so this is basically Hopper's approach to sequence-to-sequence modeling, and we're experimenting with it. And lastly, Hopper is hiring. So if anybody here is interested in really awesome data science work, we have a great team. So yeah, come talk to me afterwards if you're interested. Thanks.
And are you hiring?
Yes, we are hiring.
You are hiring.
Yes.
Oh my God, you are hiring. Thank you very much. Next in line is Sean. Sean Q. He's the director of machine learning at SmartBid.io. One fun fact about Sean is that he likes barbecue so much that
Hi there. Thanks for the introduction, Yossi. I also do other things than brisket. Whoops. Good. Where would I be without my beautiful slides? I stole this deck and cut it apart and reassembled it to make a new point. And as a bit of geezing, which I think is the technical term for what Yossi was doing earlier, I went to graduate school here in a lab that was about 80 feet that way and about 15 feet down and is no longer here. Many people in that building actually have offices in this building, but I went out to build systems and do software, which is how I wound up at SmartBid. SmartBid is a company that's bringing machine learning. Our CEO loves to say AI, but I still have bad connotations from AI from a long time ago, so I'll say machine learning. You can just substitute. But we're applying those technologies in the architecture, engineering, and construction industry, AEC. I will probably not use that acronym again, but these are the people that build the buildings that we work in, that build the houses that we live in. The interesting thing about that business in particular is it's a huge business. We're talking a $10 trillion business plus worldwide. I don't know how they capture the value of everything that's going on in China, for instance. And not only is it huge, but it's actually quite dangerous. I don't know if anybody in the audience other than me will admit to watching people fishing crab in the Bering Sea, where they say this is the deadliest job in America. That may well be true, but there's only a few hundred of those people exposing themselves to risk. In the construction industry, it's responsible for 20% of the deaths in the workplace in the US. That's a lot of people, and it's a lot of risk. If you add to that the casualties, which get underreported now, perhaps from the military, but Casualties, including getting injured, everything from stubbing your toe to having something really heavy dropped on you. An injury happens to a worker 1 out of 10 per year. Deaths on construction work sites have been going up steadily since 2007. That's probably because there's more construction, not because people are being unsafe. But it means the problem's getting bigger. So some, as it were, fun facts you might know about the construction, might not know about the construction industry. First, although what they do tends to be kind of manual and kind of dangerous and physical, they are really into large amounts of data collection, data capture, and let's say collecting media. So a typical construction site will be capturing photos constantly, maybe capturing video. We'll have a ton of additional project documentation that goes with that. Some of that is available across a number of systems, which probably mean nothing to people in this room, but whoops, that part doesn't work. Go back, please. Yes, thank you. Remember me not to click. Autodesk, you've probably heard of. They have a system for integrated information capture for the construction industry called BIM 360. They have a substantial part of the business. They have millions and millions and millions of records in that, all of which could be repurposed to doing something useful if you can integrate with it. And that integration is something that we do along with building our own applications. So we tried to bring all of that data into a single system. This is the enterprise software slide because it says workflows, analysis, and feedback. A key point to this industry is this is very much an enterprise software sale. These are not 10 to 20 person startups, not 10 to 20 person high-tech companies. They are places where you have to build bulletproof software in order to deliver value. And so we try to span that gap. And in fact, the reason that I'm at SmartVid, leaving another startup that was founded by friends, at which I was a day zero employee, is because these guys already had a product in the market and needed to add machine learning to it. So that's why I came on board. So we do everything from photo and video integration, also structured data out of systems like Procore or Autodesk. We apply advanced speech and image recognition technologies to that, and then try to deliver value to the senior staff at a construction company that lets them address their risk issues. All right, so we've got 5 million images from our customers analyzed so far, and now for the slightly sexier part, I will show you some pictures, okay? Now, one of the things we do is about productivity and doing progress reporting via speech recognition, and that's exciting from a financial point of view. But the part that's most interesting really is reducing the risk to workers. So we have the ability to look at all the photographs that are coming off a construction site, which could be hundreds a week, could be thousands a week. The new, well, they used to call it the Wynn Casino in Everett, and I forget what they're calling it now, produces a lot of data photographically every week. No human being is going to look at it all, and yet it's full of useful information. The gentleman here on the left isn't wearing his proper safety equipment. You probably could guess that. Now, he does have a hard hat, but he's missing his safety colors. He doesn't have gloves, and I'm not sure about his shoes. So we have an AI solution, an ML solution that we've named Vinny, because Vinny was the name of a supervisor on an early site that pointed out the value of some of this to us. And we make a number of observations about pictures, photographs that are contributed now. For instance, you see the gentleman on the right here who's got his hand extended towards the girder. He's not wearing gloves. Turns out hand injuries are the #1 kind of injury on a job site. And although it might not lose a life, you might lose weeks of productivity. And in this industry, that translates directly to financial risk, because the people who do these jobs are actually very hard to find. And when you lose one, you put your schedule at risk. And if you're in a $10 trillion a year plus industry, there's a lot of money flowing. So it goes both ways. Sometimes you do well by doing good. In this case, we're already looking at a number of things related to safety. We have a bunch of other stuff under development, and I won't read it to you. But let me make the point on the bottom right. That does not look like a safety hazard, right? It's just a bunch of junk sitting on the floor. You might imagine that it's a trip hazard. It turns out it's correlated with projects that are at risk for safety, because if there's junk on the floor, there may be other problems going on. And that gets to what we do with a total pile of data. So I'll show some more pictures just for quick examples. This is a picture that was not taken for purposes of looking at safety. It's taken at a distance, but when you zoom into it, you can see that the two people on the right have personal protective equipment problems. One of them's not wearing gloves, and the other's not wearing a safety vest. Whoops, go backwards. Construction sites are complicated, and they're full of large moving pieces. There are a couple of moving pieces on here. There's a lift in the foreground, that's that blue thing. There are two people that are standing relatively close to it. Okay. There's also a large crane in the background. Fortunately, in this case, there's nobody standing close to it. We had a report from one of our customers recently that they lost a worker being pinched between the platform and the tracks of a large mobile crane because the operator couldn't see him, and they didn't, the person who was killed didn't realize that they were in danger. We don't expect to stop that problem in real time, but we'd like to identify projects where people are standing too close to equipment so we can direct attention for training. All right, and backing up a little further yet, there's all kinds of dangerous things going on here. The Wile E. Coyote thing of having a piano fall on you can more or less happen on a construction site. All right, so tons of raw data. Anybody who's ever managed a project knows that you don't want to look at the raw data. There's too much of it. So this process of generating observations about safety and other things from pictures, we need to roll up into information that's actionable. And there's really three stages of that. We do simple reporting, which seems simple, but they've had no access to it previously. So we can tell them, for instance, whether they're taking enough photos of a project to ensure the safety. It's a little self-interested, but it turns out to be correlated. And we can tell them for each of their individual projects how they're doing on their PPE compliance. Now, if you're a safety manager or a company like this, you want to direct limited resources to go deal with the people who are at the sites that are at most risk. This helps with that. But to make it really actionable, it's really better if you can roll it up into a dashboard. Now, this dashboard was created in conjunction with people we're working with at Shamet, which is a large local construction company. And he wanted a dashboard that would reflect his view of how the data should be organized to tell him how to send his teams out to look at things. So classic dashboard, some of it's just roll up from the reports that you saw on the previous slide. Some of it is other things, but it focuses his attention on the projects which are red, which tend to be the ones that have the lowest PPE compliance. Sometimes they have the lowest number of pictures per month, meaning he doesn't have visibility. In all of these cases, what he wants to do is send his teams out to look at that. So we go from way too many photographs to look at to reports about the photographs, which of course you can click into if you want to see the details. But C-level executives never want to see details. And at the C-level, dashboards where they can say, hey, we've got a problem in Northwest Virginia. All our projects there are in trouble. From a safety point of view, we should go look at those. But where we really want to go is predictives, right? It's good to be able to say these projects are doing better than these other ones. Would be really nice to say that project over there, we think there's a significantly increased risk in the next 3 weeks of there being an accident. Perhaps you should deploy more resources there. And at some point, we'd like to be able to say what kind of accident. Now, everybody knows, I think, in the machine learning business, the problem with this kind of thing is you're predicting the infrequent, right? Because bad things don't happen that often, which means you need a lot of data. So we started by working with Suffolk, which is one of the largest construction companies locally, and they gave us 10 years of their back project data, uncensored, along with all the outcomes from that period of time, so that we have a chance to correlate both their business data from structured sources with what we've pulled from photographs, with weather and other things, and build a model that will predict with significant lift whether next week is at a higher risk of accident than this week. The problem, of course, is Suffolk has its own business practices, and they're not the same as, say, Turner's, which is doing a big project right next door, or Shamit's, which is doing a project around here somewhere, since it's Cambridge. So back to the central problem, I think, for all of machine learning, it's about the data, right? I'm probably biased, but modeling is hard and fun, but you can't do it without the data. So we formed with our co-founding member of this, Suffolk, local construction company, an industry consortium, which is all contributing data to the one project so that we can agglomerate the data across enough, agglomerate, great word, aggregate the word data across enough different sources to have a shot at making predictive models which are cross-industry. So if you happen to be from a large construction company and you've got data you'd like to contribute, come talk to me afterwards. Some of these companies are very large. Like Bouygues is a French construction company. They're one of the largest construction companies in the world. I'd never heard of them before a month ago. But sitting at the table at our first organizational meeting for this, I did a quick count, and there was over $10 billion worth of business interests sitting at the table. This is a serious problem. And if you have the highest death rate in the country from your business, it's worth some serious effort. Now, you can probably tell that's my slide, not the CEO's slide. We are looking at a lot of different kinds of data. We look at text that comes out of systems of record. We look at extracting text from PDFs, documents, construction plans, whatnot, that are sitting in document repositories. We look at the photographs. We take video from which we can extract images. We can also extract the speech from the video and then do natural language work on top of the speech. And then we have interesting structured data which comes from our customers. It's interesting in part because it's different from every customer. None of them have the same back-end systems. All of these systems need to be tailored together into one. Well, when one guy says, I had a medium-sized project, if you're a 100-person construction company, that might mean a house. But if you're Suffolk and you say that, it's an office building. Reporting medium isn't enough. We need to get to standards across this industry to help us parcel out where the risks really are. So lots of work going on in here. The data flow is complicated. One of the co-founders looked at this slide as I was sending it through the local Slack channel and said, is that hard to read or is it just me? And it's hard to read because there's a lot of it. And this is skinnied down. You should see the one that's on my whiteboard. Okay, so this is about machine learning with impact. I came to this company because we can have an impact. We collect domain-specific data and build the partners. I'm almost done. I went way over my original 10-minute budget. I'm going to say those 3 words.
Yeah, I have to say that in Israel, we have a very small country. Yeah. Every week, 1 or 2 people die every week on construction sites. And it seems that we as humans, we cannot learn from our own mistakes, right?
We had somebody die within, I believe, a half mile of here within the last 6 months in construction.
Yeah.
It's a tough business.
Yeah. Thank you very much for saving so many lives.
Well, not yet, but we're working on it.
Yeah.
And thank you for cutting me off so graciously.
Thanks. Our next speaker, Praneeth. Fun fact about him is he likes to eat. He likes to eat a lot, right? He doesn't show much. You're supposed to be much bigger, but good for you. I've met him last week during the demo days. He's working on a very interesting project that I think all of you should listen to and learn more about with deep learning. Let's put it in.
The top button. There. Oh, you're good. Cool.
All right, so that's my lab. I'm a student here. I think.
It's not for that.
No,
you need it.
Okay. Sure. All right, so this is the landscape of the problem that I deeply care about. It especially shows up in the healthcare industry, but it kind of generalizes to the financial and the security sector and many other places where there's going to be inter and intra-organizational collaboration. So, for example, there's a cartoon that shows data that is siloed away across local health centers. And then the main issue is everyone can do their own modeling locally, but they're not able to pull the data. Why? It's easy to guess. Privacy is one of the biggest issues with distributed data in a lot of industries, and it's highly regulated. It's being even more regulated day to day. And whenever regulation is catching up so quick, the technology is moving very quickly as well. So that's the setting, and this is the problem. So you've seen the landscape on the constraints. The problem is, how do you train neural networks or do deep learning without sharing raw data? So that's the big problem. We've done a lot of work in our group on this. And I will skip the slide, but basically this is motivating that it's not just intelligent computing and AI or any kind of eye that you're doing with the machine, but also the issue of safety, fairness, being unbiased, and privacy and security that need to be taken into consideration when your data is distributed. There's a ton of regulation, and then there's more coming. This is costly, so companies care about this a lot. Even a single breach is going to be tens of millions of dollars at the least. There's been a lot that's happened recently. If you imagine, this is a kind of a freaky picture, but from a newspaper. So if you imagine just the location data, the amount of information that would tell about you is highly personally identifiable. It doesn't matter if you're a school kid or a housewife or a working professional or an old retired person. It's just one variable that tells a lot about you, and there's a ton of data about you all over. So this is the overall setup. We got distributed data. We want to have a solution that caters to regulations, and it needs to have an incentive for people to use it. It should be easy to use, and then it also needs to have the computational benefits of being efficient and not consume all your data plan just because you're running a model on your phone. This is some precursor in history. We've been doing some automated ML. A lot of people might have heard about this buzzword anyways. So there's been a little precursor as to what motivated our work. In terms of what's out there, there's three broad approaches to understand the landscape if you're new to the field. There's anonymization. It doesn't work. If someone thinks it works, they're being careless or maybe ignorant. Obfuscation, basically adding noise. Encryption or homomorphic encryption, which is highly secure. This doesn't work, so I'm not going to talk about things that don't work. As far as what we do, we call it SMASH. The approach we do is called split learning, split and then split deep learning. There are different variants of it. This is the only technique that basically does some amount of data protection, does not share raw data at all, but is also able to train neural networks and not do just basic statistics or modeling low-level tasks. So these are the different techniques, putting names to what we've seen before: obfuscation, differential privacy, homomorphic encryption, where you convert your data into ciphers and do parallel operations that do addition or multiplication using some weird operations on your ciphers. But when you decrypt it back, you're going to get the real solution. It's extremely secure, but it doesn't scale well because it's highly, highly computationally intensive. Split learning, that's what we're talking about. So this, again, been motivated by federated learning that Google AI came up with. It came up when it came out, it was very much ahead of its time. It didn't really catch up. Right now, it's pretty viral in the distributed learning area. All they do is every entity trains the entire deep learning neural network. So think about it. If it was your cell phone and you want to run a ResNet 100, you're like training more than 60 or 70 million parameters. So it's going to eat up a lot of resources. It's not highly resource efficient, but otherwise it's a great approach. The data doesn't leave, and the models are aggregated, and there's an upload and download of individual models that are being learned. So that's kind of a motivator. And as far as split learning goes, I'll show you the results first, and then I'll give you a quick slide or two on how it works, at least the sense of the idea. So split learning is in terms of computational efficiency, but if you look at plots for communication efficiency or memory efficiency, it's extremely efficient, kind of drastic compared to federated learning. That's our project page. There's a ton of information out there. So what is it that we're doing? This is giving some more numbers to the plot you saw. Pictures are better, so I'll skip that. So this is the overall idea, by the way, in the most vanilla sense. I mean, we've done experiments with 500 and 100 distributed clients, but this is in the most vanilla sense. We literally split the neural network, and the layers are shared by distributed parties. As far as the training goes, because the technique for training, without sharing raw data, say Alice and Bob, you heard this a lot of times, we forward propagate, and then whatever comes out of the green split layer, we just pass that to the other distributed entity. The other guy runs with it. So it's like a relay in some sense. And then he gets the predictions, and then during the backprop, just the gradients get communicated from the split layer. So that's the essence of the idea, where the data is not leaving either party. There are different variants of this depending on the sort of communication or network topology you're working with. So this scales up to if you have like a bunch of Alices, or if you had peer-to-peer and you don't have a Bob, like a server, and everyone's peer-to-peer. There's different variants of that. This shows, the second picture, for example, shows a variant where the input data nor the labels leave the entity. Both are with the same data, just the middle layers are being shared with the other entity. He's just doing intermediate computations for you without linking the raw data or the labels, for example. We've done an additional patch. We call this no-peak NN. We're kind of excited about this approach of split NN, where we also ensure whatever is leaving, the activations or the gradients in terms of the communications and the distributed learning, we try to reduce the correlations of that data, of whatever is being communicated with the raw data itself. So if someone even interjects that via some network or like a cybersecurity attack, he wouldn't be able to reconstruct the raw data. So all he has is something that is useful to go forward, but it wouldn't be able to reconstruct the raw data. So that's the sense of the idea. We have some theoretical work, but these are examples that show how the correlation is getting reduced. In traditional CNNs, the correlation is extremely high in mid layers. It's like over 90%. Ours reduces extremely well, even from the first epoch itself. So even during the training, you're not able to reconstruct anything if someone interjects the data. We maintain similar accuracies. And this is a quick experiment. So the one before was like a real-life healthcare data set. This is like the typical MNIST that is showing that you're not able to reconstruct the raw data using whatever you're basically communicating, even using the state-of-the-art networks of some sense. So that's the project page. It's a lot of friends, collaborators, and people to keep me going. Thank you.
Thank you very much.
Okay. Thank you.
I think as you learn more about deep learning, you'll see that data privacy and protection is a huge problem. And this is one of the more creative ways I've seen to actually attack this. The next one to speak is David. David from AirWorks. The fun fact about David is that he's happy all the time. Not really clear to his peers why and how and what he's taking, but I want some too.
Yeah, absolutely. Happy to share happiness.
Here, everyone, mic for you.
Yeah. Let's see if this works. One second. Perfect. People hear me? Is that okay?
No, you need to speak up.
All right. Yeah.
Really loud.
Oh, perfect. Okay, no problem. Hey, everyone. Nice to meet you. My name is David Morczinek. I'm the CEO and co-founder of a company called AirWorks. Like a couple of my colleagues here, so feel free to share and ask them questions afterwards. So AirWorks essentially is an aerial intelligence company for the construction industry. In short, we help engineers and land developers save time and reduce risk. But before I tell you more about it, I brought a very short video to set the scene.
It is challenging, complex, and often chaotic. To do my job, I have to aggregate various sources of site information, which can take too much time and quite often be inaccurate. This can lead to massive inefficiencies and delays, but it doesn't have to be this way. When AirWorks came to me with their site analytics software, I was interested. AirWorks helps me survey sites 10 times faster. With this technology, you can make more accurate cost estimates and assess risk earlier. It's time for 21st century construction, and AirWorks is making that happen.
So when we started looking into this problem, we found out that Mike here is not the only one with it. In fact, in the US, there's about 300,000 civil engineers that are assessing, planning, and estimating construction sites every single day. Their main job is to analyze the future construction project, create the design, but also make schedules and planning and cost estimates that stay on track and on schedule. Now, in order to do that, as you can imagine, and as everyone, they need data. They need to know the exact measurements of a current construction site in order to create a future plan. The way to do that today is they work with a surveying team like this. The current state of the art is to take measurements for each point, point by point, with an optical instrument that's mounted on a tripod on the ground. If you look at how this has been done 100 years ago, it doesn't look much different, and it's still the same exact technology. Yeah, a bit of automation, but not that much. And essentially the problem is if civil engineers want to use that technology and create an existing conditions drawing of a current site, they're looking at 2 weeks to even get a quote. They're looking at 2 months to receive any kind of data so they can start their planning. And on top of that, they're paying up to $50,000 for that work. Now, this is the view out of my former dorm room here at MIT. And I'm sure many of you know this. The impact is that we have construction all around. And what I'm learning, and if you look at the statistics, is that only 1 out of 3 projects is on time. And all that is due to bad data. All our clients tell us they start designing before they even have survey data, because surveyors are behind, over 2 weeks or 3 weeks behind on their design. On commercial construction, it's even only 1 out of 9 projects that's on time. Now, our vision at AirWorks is that anyone can get updated engineering drawings of any projects and of any site in the world with a click of a button. The way we want to do that is we want to give our clients the chance to specify an area. They can access all kinds of available site data, and they can ideally download ready engineering drawings with the click of a button. That would be a game changer in the $7.7 billion surveying market. It's a huge industry, as has already been previously explained. Now, how do we get there? Part of the solution, as I've already mentioned, is aerial data analytics. In the past, a surveyor has been able to collect about 500 data points a day. On a traditional site, therefore, they'll be about 3 to 4 weeks. Now, with drones, we have the ability to collect 20 million points of data in 1 single hour of flight. Together with some ground control techniques and modeling, we can make sure that these points have the same accuracy as surveyors traditionally were able to get. But it also comes with a problem. What do we do with 20 million data points? No one needs that. And that's what we see. The first steps of the process, you have to capture the data, right? And you have to stitch the images into a model. And most of that has already been automated. But what we see now more and more, that our clients spend 80% of the time, and hours, in going through aerial images and drafting and labeling things by hand to make sense of that data and put it back into the systems they used to use anyways. So in our experience, the benefits of drones essentially in the construction industry have been offset largely by now the efforts of labeling and tracing data. That is very expensive and time-consuming. And that essentially brings us to the core of what we do. We look at aerial data from any kind of source, mostly drones, and identify and detect and measure objects of interest. While a traditional engineer would, for example, take about 40 hours to label and create an engineering drawing from that data, our software will be able to do that in about 30 minutes. Now, that's very different to what all the other aerial drone companies are doing out there, because essentially, they're only creating the unlabeled data sets, where engineers have to do all the work themselves. What you're looking at here is the first output we developed last summer of a fully autonomously created drawing. On the left side is the input that we gave to the model and to the machine learning engine, essentially. And on the right side, you see the output. What is labeled here is already 5 different layers. So we can identify buildings, we can identify roads, sidewalks, and topography fully autonomously, without a human ever being in the loop. And this is running in 30 minutes. Now, the challenge is, of course, every construction site looks a bit different. There's different layers. There's different things engineers are interested. If we can imagine, a typical drawing has between 20 to 30 layers. But we've already come a long way. You see things here. You see the first 5 layers here. And very recently, our team has worked on road markings and paint lines on the streets. If an engineer was to label this parking lot, he would spend over a full day in doing that himself. That can be done now in a couple minutes with our software. We're also able to identify objects such as manholes, as you can see here. There may be up to 30 to 50 manholes on one single site that people are looking to redevelop. And going through them and identifying them can be very time-consuming. We're adding drains and fire hydrants and light posts as we speak. So hopefully, by the summer, we'll have about 10 layers that will help us to launch our software to the public. Our ultimate goal is to create this drawing fully autonomously at the same quality as surveyors would do it all around the world. Now today, we've already started working with clients, and we're showing that this technology can work. Most of our drawings are still created manually on individual projects, but this helps us to build our training data set. As you've already seen, you need a lot of data in order to build confident predictions. It's sometimes easier on the large-scale objects like roads, but it's very difficult on individual objects. Also, lighting conditions differ on every project, so we need really a lot of data to make sure our predictions are correct. By this summer, we want to have our first software ready and deploy this around the world. Essentially, the idea is that anyone can upload a data set coming from a drone or an aircraft, and we spit out a CAD drawing on our platform. This will help clients even to make better estimates, to make better predictions, and maybe even decide to buy one project versus the other one. Ultimately, this is a way to democratize engineering drawings and map the world in very high accuracy. And today, what you see on the left is essentially a traditional output that we would create today. Our end goal would be to even go in 3D. It's a much more challenging problem, as you can imagine. It's hard enough to predict objects in 2D. We're ultimately looking to build architecture models and architecture and civil engineering models in 3D so people can really map the world and start designing and remodeling of what they're doing. But for that, we have a bit of work to do. And so we hope what we do in 2D is going to get us there. Yeah, thanks. That's a quick snapshot of what we do.
Thank you very much. Thank you. The next speaker is a very short one, Philip Tester. It's not a job description, it's actually his name, Philip Tester. One fun fact about him.
All right, thanks. I'm actually, yeah, it's right here. Yeah.
And we have, what's the cable? Here it is.
Okay.
You have HDMI.
I do. Yeah, hold on just a sec. I need to. Okay. Okay. Let me refresh this. Yeah, thank you to Yossi and the Missing Link team for setting this up and inviting Cloud Factory to participate. Really happy to be here today. Free pizza is always great. It's also just cool to hear about this topic of how AI is changing the world. And we've already heard some really cool things from like construction site safety to optimized flight purchasing, which is great for me personally. The topic of how AI can change the world is actually at the heart of Cloud Factory and why we exist. Maybe in kind of a different way, which I'm really excited to get to talk about. So this will be a little bit different because we're not a software company per se. We're not even really a data science company. It's actually a little bit different than that, but still a key part of the AI ecosystem. So what is Cloud Factory? It's a people company. Effectively, we offer a managed workforce as a service. Which is really powered by technology, but the idea that you need teams of trained and dedicated people to support core data processing as well as producing training data sets to develop machine learning models. And that's a really wide variety of use cases for us, so effectively the humans in the loop. And the use cases that Cloud Factory can help support, the ones you might expect in computer vision and NLP, all sorts of image and video processing from basic image labeling to bounding boxes and polygons and semantic segmentation and even 3D point cloud as well as sensor fusion tagging arrays. In natural language processing, again, just structuring text for conversational intelligence, for chatbots, for smart search, any variety of use cases there, just a subset of our customers there. The idea is, though, why does Cloud Factory need to exist? Because data can be labeled without a team like that. Well, humans haven't been completely automated out of participation in the development of models just yet. Our bet is that today, just like tomorrow and for the foreseeable future, human intelligence supplied by actual humans is going to continue to play a key role in providing the data that enables models to be developed and be high-performing, and for the products based on them to be brought to market with speed. And there's a certain portion of that that could potentially be automated today. That'll continue to happen. There are online and unmanaged crowds of people that are often good for kind of prototyping or working on highly repetitive tasks. And there's certainly a portion that is too specialized and requires a certain amount of domain expertise or skill to do. But the middle portion of that is actually most of it. And that's the thing where it's tedious grunt work that can be trained and taught to a reasonably bright and motivated person. And it's too time-consuming for very capable and highly expensive data scientists and engineers to be working on. So Cloud Factory basically excels at that task. Talk a little bit about how we do what we do just quickly before I get to the why. It's a combination of people, process, and platform. So on the people side, we're totally vertically integrated. So Cloud Factory today has delivery centers in Kathmandu, Nepal, where we were founded, and in Nairobi, Kenya. All told, we have about 5,000 full-time workers. And we do everything from interviewing them, assessing them to do a skills mapping, assigning to customer engagements based on fit, training them on specific process and guidelines, and then coaching and giving feedback over time. So everything, soup to nuts, on the people side is Cloud Factory. The process that we've developed to do that includes methodologies for just quickly onboarding and ramping up learning, from daily sprints to working in pairs, iterative feedback cycles. We have developed sort of a Pomodoro technique for the work that we do. So our teams leverage sort of a burst break model to kind of optimize focus and engagement over a long work period, because these can be really dull tasks. And then on the platform side, we certainly have developed some really cool technology that help us do this. A reputation scoring algorithm, an intelligent task routing mechanism that takes into account multiple customers, thousands of active workers at a time, all with various skills and different capabilities within those skills, and optimizes for client priority and a bunch of other things, as well as some predictive performance modeling, which is some of the really new stuff that we're working on. So that's a little bit about what we do, and the net result of that is for our customers, what it creates is what we call cloud labor. It's this idea of like a really agile team that can adapt to processes over time because it's people. It's easy for them to scale because they don't have to actually go out and hire people and give them a place to work and a workstation and teach them how to do it. We've already got the playbook. We've got the trainer who can train them up, and produces high quality data, and that's value for our customers, and that's great. There's another layer to it for Cloud Factory, though, and that is that Cloud Factory exists to actually provide the work to the people that are doing it. And that's the mission behind Cloud Factory. Actually, the vision for the company is to provide meaningful work to 1 million people in the developing world. So we use that technology to connect people in places like Kathmandu and Nairobi to this digital economy. And there's an abundance of talent there, and not as much opportunity to take advantage of it. And so part of our worldview is that talent is equally distributed, but opportunity is not. And so Cloud Factory exists to help to bridge that gap. The cool thing is it's a virtuous circle, because our goal is to provide good work to people. We pay well, we invest in them as people, we create communities for them to work in, we offer opportunities for development and growth within the company to learn hard technical skills. This is actually upskilling people while paying them really well and providing a really good work experience. The net effect of that is it's a good job that people want to get, and then they want to keep it. So they're intrinsically motivated to do really good work. So our customers get motivated people working hard to produce good data for them. That helps their business. In turn, that enables us to provide that work at scale. So we're building the technology today to continue scaling that out around the world. And that's the real human impact of this for us, is like we get to invest in those people and communities. It's even cooler when sometimes that comes even like fuller circle. For example, recently there was an instance we helped a client develop it was an ag tech customer, and we helped them build a computer vision model for crop performance. So in Kenya, there are these groups of like women subsistence level farmers who can use their phone to take pictures of their farmland and get predictions about crop yield and actually optimize the way that they're farming based on that. And it's just really awesome for us to be able to reinvest in those communities with some of the products we develop. That's it. Thank you.
Thank you very much.
Yeah.
By the way, do you have any fashion tagging tasks for my kids?
Oh, yeah.
I can make some money?
Yeah,
Yeah, you
sure.
have?
Are they good at it?
Yeah, they're very good at it. Our next speaker is Ivan.
Yeah. I was going to take that with me.
That's okay. Culinary affairs in Iterative Scopes. And Iterative Scopes is a very interesting medical company running from Boston in a non-convenient topic, right? Yeah, I'll let you explain on. Yeah, this is it. This is just yeah.
Hey everybody, my name is Evan. As Yossi said, I do regulatory and compliance work at Iterative Scopes. We're a company, early stage startup here in Cambridge. And what we do is, as you can see on the slide there, computer vision analytics for healthcare, which is a broad picture scope of what we do, but I'm gonna focus more granularly on our immediate efforts within gastroenterology, which is our first step towards achieving that big picture. So as some of you may know, colonoscopy is the gold standard for colorectal cancer screening. Colorectal cancer being the second deadliest form of cancer in the United States currently. And because of that, insurance providers require it at a certain age. If you're identified to be at risk, you have to have them perform more frequently. However, despite being such a high throughput procedure with over 15 million of them being performed in the US every year, about a quarter of those precancerous polyps that they're looking for, or cancerous polyps, are actually missed during these procedures. And that's due to a variety of reasons ranging from just difficult to see growths, poor prep by the patient themselves, or clinician fatigue. So this is a problem that clearly there's a disparity in the level of care that you might be receiving when you get a colonoscopy. If you're at 25% chance of having a cancerous growth missed. So our founder, John, who used to work at the Ministry of Health in Singapore, was well aware of these metrics and decided to apply computer vision to this problem to try and reduce these rates and better the outcomes from colonoscopy. So what we're building currently is a medical device that we're calling Scout. To give a little context about like what you're actually seeing on the screen there, what physicians look at when they do these procedures is essentially that video screen without the box, this octagon of a video feed, and they run the scope through the colon looking for these growths that they remove in real time or mark for later to remove during a later procedure. However, like I said, a lot of them are hard to see. The one there is a particularly difficult type of growth to see called the sessile serrated adenoma, or SSA. So what we've been working on at Iterative Scopes is developing a device that integrates with the endoscopic equipment within the room that can automatically detect these growths and highlight them, for example, with like the bounding box in the picture there in real time. So this has a few unique challenges compared to some other products, but a few of the big ones are achieving it in real time. Yossi mentioned a product earlier, AI Doc, a company that works on radiology and CAT scans, automatically identifying problems within those images. However, that's post-procedure, so one unique challenge that we face is doing this in real time, getting the inference down fast enough so the doctor can actually use this during the procedure, as well as the data acquisition process. Colonoscopies currently aren't recorded, so we have to form data partnerships with hospitals and physicians, et cetera, and get patients' consent to record these procedures. and then build our model and train it based off of that. So our ultimate vision right now is to build Scout and have it cleared by the FDA so we can market it, get it into hospitals, and start decreasing the rates of missed polyps during procedures, better patient outcomes, and reduce costs for patients that would potentially have to pay for expensive cancer treatment if a polyp were to be missed. But beyond that, we're also working on a cloud-based data analytics platform that integrates information such as EHR data, among other types of data, with the data insights that are created by our product Scout to create a comprehensive platform for unique data insights that provide value to physicians, potentially pharma companies, biotechs, et cetera. Right now, we have some excellent partnerships with physicians in hospitals, both within the Boston area, some of the names you might recognize on there, as well as throughout the United States. And we're currently focusing on building more as we acquire more data to improve our model. And as I said before, we're really looking at this not just for gastroenterology, not just for polyp detection, but for data as a service in the long term, as well as applying this technology to any procedure that uses real-time video imaging for detection or diagnosis. There's a few other applications that a product like this could achieve, such as beyond detection diagnosis, implementing histology data, pathological data, and morphological data of those polyps to help physicians have even more insights in real time. Currently, as I said, we're a small stage company. We have about 14 employees. A lot of them graduated from MIT. Some have worked at the Media Lab. And we're currently in the midst of, we just closed off a second seed round, and we're raising a Series A at the moment, focusing on data acquisition, and then our eyes set on FDA clearance of Scout early next year. Yeah, that's it.
Very cool.
Thanks.
Thank you very much. When is this going to be launched? When is this going to happen?
Oh yeah, so hopefully early 2020.
2020. Okay,
Yeah.
not far away. Thank you very much. We have two more speakers. The next speaker is called Kfir. Kfir from DeepCure. Two fun facts about Kfir. Kfir was an Apache fighter pilot in the Israeli army. So he's a very smart and agile guy. And the second one, he's married to the head of AI of Open. Now, two deep learning companies, imagine what's going on at home.
You don't want to know. Great. So some of the speakers already spoke about kind of challenges in healthcare. We at DeepCure strongly believe that one of the biggest challenges in healthcare today is the cost and time it takes to make new drugs. So I believe these stats were pretty much all over the place. But to make a new drug today costs $2.6 billion and more than 15 years of development, which is just insane if you think about it. But worse than the fact that we are wasting a lot of resources, we are also stopping development of new drugs that are not being developed due to resources being pointed towards existing programs. And we're not delivering drugs fast enough to patients in need. But I want to share a first example about how DeepCure is really changing that and trying to solve the problem. So one of the first case studies we did involved a protein or a therapeutic target from the hepatitis C virus. Until a decade ago or so, hepatitis C was killing 500,000 people around the world each year. But in the last few years, a few new drugs were introduced into the market, and HCV is almost completely cured today. What we did in this experiment is we tested our algorithms, the AI platform we developed, against this specific target. In order to do this and to make kind of a fair test, we excluded all the data about the specific target, about the known drugs, about any of their precursors, and we tried to see, can the algorithms rediscover any of the known results, and can they generate any new interesting ones? So we ran our algorithms, and in just a few days, a bit under 2 weeks of computation, we were able to analyze a list of 1 billion molecules. And I will speak in a second about how important it is to look at very, very many examples. And at the top 30 out of 1 billion, we found the known drug. It's this orange molecule over here. And other than that, higher ranked than the known drug, we found several other molecules. They all received better scores from the algorithms. So what we did was we went back and we looked at the literature, we looked at patent databases, and we tried to understand whether someone tried any of these molecules. And the answer is no. They don't exist in any patent database, they don't exist in the literature, which means that they were just outside of the scope of traditional pipelines. So this is very interesting, but the question is it actually working? So what we did is we took the results, both these few molecules and a list of other ones, and we compared them. We compared them using existing models, physics-based models that are much more expensive, computationally expensive to run. And what we can see here on the right, the blue thing is a protein, or a part of a protein. And the colorful molecules are basically potential drugs. And this kind of very nice overlay, this shape fitting, suggests that all of these new molecules are a good potential drugs for the same protein as the known one, which is the fat orange. And on the left, we can see the distribution received by the models that suggests that they can truly identify the best molecules out of the database. So the last step we did was to look back at the development of this drug and analyze how much time we could have saved in this development. We realized that to get to the same point that we reached in just a couple of weeks took roughly 2 years for the pharmaceutical company. In those 2 years, more than 1 million people died. So we could have saved all these lives, and of course, a lot of money, which is slightly less important. So this is just one example out of roughly 10 different examples we already did at DeepCure. And the reason we started the company, and we actually started it right over there in this building, was that we looked at the industry, we saw this huge need, and we thought that there are two main goals we can achieve with deep learning, AI, machine learning, call it however you want. The first one is expanding the scope of what is possible. And what do I mean by that? So traditional drug discovery starts with a drug library, something like 1 million compounds, 2 million compounds that are all tested in an automated fashion against a specific target, a specific protein. However, the space of potential drugs is estimated to be 10 to the 60. This is 1 with 60 zeros after that. So extremely enormous, something we can't really comprehend. But what we are trying to do is to just push the limit on that. DeepCure's platform today can analyze 10 to the 12 unique molecules. That's 1 trillion different molecules for any individual target. 5 to 6 orders of magnitude more than currently possible. And in this industry, just testing more means that the likelihood of finding a good drug or the best drug is much, much higher. But the second goal and the second piece of the puzzle is the fact that the process itself today is extremely inefficient. So to find a drug or to make a drug, we need to solve or to answer many, many different questions. A molecule has to be potent, it has to be selective, it has to be non-toxic, it has to be soluble, and so on and so forth. There are roughly 20 different parameters you are trying to optimize for. But the process today is that you have a group of very talented chemists with a lot of experience optimizing each property at a time. So they start with binding to the protein, and they optimize the potency, and they try to make a selective one, and so on and so forth. And this is a very kind of local optima approach, what we as computer scientists call a greedy algorithm. However, DeepCure's platform allows us to change this into a multi-parameter optimization approach. So suddenly you don't have to solve each parameter separately. You can co-optimize them all together to find a much more holistic solution, which means that you are much likely to find the optimal drug at the end of the process. So let me walk you very briefly about the technology behind what we are doing. And there are 3 main components to that. The first one is just the search space, or basically a database of potential drugs. In order to search for one, we need to first build this database. This is what we are doing internally. We are building a database of 1 trillion different compounds that were optimized both for the diversity, because just testing many different things is not enough. You really want to expand and explore the space, but also for synthesizability, which means that we can actually go test and make these compounds, which of course is very important if you are ever going to make a drug. The way we are doing this is based on an enumeration approach. We apply known chemistry, existing reactions to available building blocks, and basically enumerating all the possible products from that. But in order to kind of expand further and to push what we already know, we use generative modeling and generative neural networks, for those of you who are familiar, in order to kind of push the space a bit further, try molecules that are not necessarily trivial for a medicinal chemist. And at the end, we convert all of these into what we call DeepCure's representation. And this is really the secret sauce of everything we do. It's a way to take a molecule, which is a group of atoms in 3D space, and represent it in a way that will be both very efficient, but also extremely informative for a deep learning algorithm. The next step is applying predictive algorithms. We use all the types of algorithms you know, supervised and semi-supervised predictive algorithms based on, most of them are neural networks, deep learning, but we also use some more traditional models. To be honest, it's not the most important piece. And we do that in order to predict all the most important properties that I just mentioned. So anywhere from binding to toxicity, ADI properties, and all the boxes we need to check in order to find a real drug. Of course, we compare them against industry standards, and I should say some of the more challenging internal benchmarks that we developed. And maybe the most important piece of our predictive algorithms is the fact that they are very easily fine-tuned. And so whoever is familiar with deep learning probably is familiar with the concept of transfer learning or fine-tuning. But in this case, it's especially interesting because when you have a general model, it was designed to find drugs for basically every protein out there. But when you work with a pharma company or you're trying to develop a drug internally, you don't really care that you have an algorithm that can predict for 1,000 other proteins. You only care about this one protein that you are trying to develop a drug for. But the available data is usually very minimal, something in the order of 100 data points, maybe, if you are lucky. So we put a lot of effort while developing this technology to be able to utilize very small data sets in order to fine-tune our general models and deliver to our partners a custom-fitted solution that is the best for their specific need. It might not be answering as many questions, but the one question we really care about, it answers the best. And finally, as you probably understand, there is a lot of computation being done here. We store a database of 1 trillion rows, roughly 1 terabyte of data. We run inference using deep learning, fairly heavy neural networks on a trillion rows. And all of that has to be super secure because when you deal with pharmaceutical data, our partner is pretty sensitive, as you can imagine. So we designed a pretty strong backend, completely cloud-based, completely containerized, in order to support all of that. We recently ran a benchmark on 30,000 cores on AWS, keeping our utilization at 100%, which was pretty cool, and not something you can do traditionally. Finally, one of the coolest things, in my opinion, and Alex, that was here until a few minutes, is the guy that developed that, is what we call Project Wolverine. Basically, a competitive environment to design, test, and evaluate different machine learning models. So as I said, you can think about so many different predictive models, SVMs, random forest, neural networks, one of the 100 different configurations you might find there. And for each of them, you have millions of potential hyperparameter configurations. The real question is, how do you find the optimal one? So we designed a platform and an environment based on Bayesian optimization and bandit approaches in order to test thousands of different models, optimize their hyperparameters, and identify the one that is performing the best for every specific task. So we don't need a one-size-fits-all, but we can find the optimal model, no matter what type it is, for the specific task we're trying to solve. So combining all of that together is exactly what allows us to address the two goals I mentioned before, reducing the cost of development and shortening the time period it takes in order to find a drug, just by pushing the limits of how many things we can analyze and how quickly we can go through them in order to find the most promising potential compound in a very big library. And just to kind of understand the scope of that, doing the same kind of computation we are doing today, 1 trillion different compounds, analyzed against just one property, not the 20 different properties DeepCure is doing, would take roughly 2 weeks of world compute. That's every processor, Google, Amazon, Microsoft, all together can give you for 2 weeks to analyze a single property. We are doing 20 of them in a few days on a small cluster internally. And combining all of that, gets us to the mission for DeepCure, which is really delivering to patients highly effective drugs that are just unlikely to be found with traditional methods. Thank you very much. Before Yossi is cutting me, we are actively looking for deep learning engineers and people that are interested in this space, so please reach out. Thank you.
Thank you very much. Very cool. So the next, last speaker that we have is
Yes.
everybody, thank you very much for joining us today. We will send an email with all the contacts for everybody, for the speakers, so you can interact and ask questions and maybe work with them somehow. Thank you very much for joining us today.
Are the slides going to be available? Huh? The slides?
The slides, I will ask the speakers to give us the slides.